Okay, so it should be recording now. So for this session, I thought we would try something different just because I think that maybe we would all benefit more from working on MCAT problems that incorporate these concepts. I've also included some YouTube videos throughout this PowerPoint that you can look at later, so you get more of that content review aspect as well. But yeah, I think like it would be helpful if we went through some MCAT-based passage problems and worked through them together. Okay, so the question is linked above. I got it from Khan Academy. And so this question is basically on cardiac pressure volume curves. And this incorporates both fluid dynamics and also concepts of pressure and volume. So I'll just give you a minute to read through this question yourself, and then we'll go over the key parts of it together. Okay, so let's look over the passage and try to bring out the key points. So basically, they're talking about how a heart pumps blood throughout the body. So in the first paragraph, we can see that they mentioned the heart can be that this can be modeled as a pump, as a fluid pump with two pressure activated valves. Also, in the second paragraph, we see that they basically describe like what is happening in each of the images in the diagram. So basically, in the first segment, they're saying that as the heart is filling with blood, it expands. In the second image, they're saying that the mitral valve, the valve at the bottom, closes. So therefore, no more blood comes in, but the heart then constricts. So this increases the pressure. And then in the third image, they're basically showing that the aortic valve, the valve at the top, is opened. And so the blood can then flow through. And meanwhile, the heart is still constricting, so the pressure is still increasing. So the pressure is still increasing at that point. And then for the last image, it's basically showing that the aortic valve then closes and the mitral valve opens. So we're basically going back to the first image in which blood is coming into the chamber and the ventricle is expanding. So the first question is, why the volume remains constant despite the pressure increase in section BC. So section BC is when both of the valves, the mitral valve and the aortic valve, are both closed, but the heart is still expanding. So this is why the pressure is increasing because, sorry, not expanding, it's constricting. And so this is why the pressure is increasing. However, despite this pressure increase, the volume of the blood still remains constant. And so they're basically asking why this is, despite the pressure increase. So I'll just give you like 30 seconds to think about that, and then we'll go over the reason why this is. Okay, so now let's go through this. Okay, so answer choices A, B, and C are not true, so that means that D is correct. So the reason why A and B are incorrect is because they both is that they both are gas laws. So the ideal gas law is PV equals nRT. However, this is not applicable because blood is a liquid. Boyle's law is P1V1 equals P2V2. And again, this only applies to gases. And this is because that, if you think about it, gas molecules are way more dispersed than liquid molecules, and blood is a liquid. It's actually a mixture of liquid and plasma, but in this case, we can consider it just a liquid. Okay, so gas molecules are way more dispersed. Because they're more dispersed, when you increase pressure, you can also, when you increase pressure, it also decreases the volume because the molecules can get closer together. However, liquids, the molecules are closer together, are like less dispersed than in gas. And so that's why when you increase the pressure, you actually can't decrease the volume. And so C is blood efflux, and this is a change in volume if the blood was leaving the heart. However, you can see in section BC in the image, both of the valves are closed. Therefore, the blood is not leaving the heart. And so that is why C is also incorrect. So the correct answer choice is D, which is liquid incompressibility. And so this is just that under standard pressure, the volume of liquids does not change. And so this is because of the reason we talked about before. It's because gases are far more dispersed and liquids are far less dispersed in terms of their atoms. And so therefore, if you increase their pressure at standard pressure rates, then you will not decrease the volume. However, keep in mind that liquids can be compressed under extremely high pressures that can change their densities. However, these conditions will always be mentioned on the MCAT. Otherwise, always treat fluids such as liquids as incompressible. Okay, so for the next question, it's based on the same passage. So during the pressurization phase, BC, what is the pressure in the narrow valve entrance compared to the wider chamber? So BC is the second image, and on the diagram or on the graph, you can see that BC, you can see that there's a rapid increase in pressure, but not much change in volume. So I'll just give you a second to think about this, and then we'll go over this together. Okay, so now let's think about this. So BC is the pressurization phase. And so this is the phase when both valves are closed. So both the mitral and aortic valves are closed. So therefore, the blood is basically not going anywhere. It's still in that chamber. And so at the same time, the ventricle is actually constricting. And so the pressure is increasing. So that's why it's called pressurization. However, there is a difference in pressure between the widest part of the ventricle versus the narrow valve entrance. And so they're asking basically what is the pressure difference between these two places? And the answer is that the pressure is actually smaller at the valve entrance. And that's because blood can flow out of the blood can flow out of the valve entrance, and therefore the pressure is lower than in the wider chamber. So in other words, this was actually Khan Academy's explanation. However, I think about this more in terms of the area, the cross-sectional area of the valve entrance versus the wider part. So this is part of Bernoulli's principle. Okay, so the major thing that's going on is the Venturi effect. And so this is the reduction in fluid pressure when fluid flows through a constricted section. So basically what this means is that in wider parts of the ventricle, the pressure is greater than in the narrower parts. And this might seem counterintuitive to you. Like if you try to think about this yourself, like I was confused at first too, like if there's a smaller area, doesn't that mean there would be greater pressure? However, it actually doesn't work like this, and this is because of Bernoulli's principle. So Bernoulli's principle is exceptionally important. It's quite possibly the most important equation in fluid dynamics. And so you really need to know this equation, but most importantly, know the relationships you can derive from this equation. So Bernoulli's principle, in its most basic form, is pressure plus 1/2 density of the fluid times the square of the velocity of the fluid plus the density plus gravitational acceleration plus height. And so what Bernoulli's principle is saying, that all of these terms in this equation are constant. So what that means is that as a liquid flows through a pipe, for example, as long as the temperature remains the same and the fluid flow is non-turbulent and the liquid is incompressible, and we also assume that it experiences no friction. But as long as all of these things are true, what Bernoulli is saying is that the relationships between these variables all remain the same. They're all constant. So what this means is that, for example, say that pressure increases. That means that velocity or density has to decrease in order to maintain the constancy of all of these terms. And so we can also use Bernoulli's equation to evaluate the changes between 2 points in a streamline, or like basically the journey of a liquid. So if you think about like a stream, at 2 points of the stream, like point 1 and point 2, you can basically assume that the relationships between all of these variables are constant, and you can use the second form of Bernoulli's equation, which includes P1 and P2, to evaluate the differences or evaluate the terms in each part. So anyways, in regards to this question, when the fluid flows through the valve, its velocity or speed increases due to the smaller area of the section. Because the area is smaller, all of the fluid is basically forced through that smaller area from a wider area. So this basically causes it to go faster. And so Bernoulli's principle indicates an inverse relationship between the pressure and the velocity. So this means that as the velocity increases, the pressure decreases. So basically, when the area is smaller, the pressure is also smaller. Conceptually, we can think about this as pressure is the molecules pressing on the sides of the chamber. So if you look at this, in BC, you can see that the chamber is constricting. And so therefore, the molecules in the widest part of the chamber are actually, more of the molecules in the widest part of the chamber are actually pressing against the sides of the chamber. And so therefore, the pressure is increasing. However, in the narrower parts of the chamber, like right here, if you can see my clicker, the fluid is actually forced through that narrow part. So that means because the velocity is increasing, that means that the molecules are all moving in one direction. And because they're all moving in one direction as they're being forced through that part, that means that there's less of them that are actually pressing against the sides of the chamber, because they're all going in one direction. So they're not all going in different directions, pressing on the walls of the chamber. So yeah, that's basically what that means. So yeah, know Bernoulli's principle. It is extremely important, and you're almost certainly going to see questions on the MCAT, unless you're like extremely lucky, that are based on Bernoulli's principle. Okay, so this is just a video of Bernoulli's principle. We'll just see like a few minutes of this, but I recommend watching the full video so you truly understand it. And most importantly, understand the relationships between each of the variables. Like, know that each of the variables are going to stay constant, as long as it's the same liquid flowing through the same part of the tube. So yeah, let's just watch like 3 minutes of this video, just so you can get that content. I'm not sure if you can like hear it. Okay, hopefully you can hear this. Okay, so can't hear it. Okay, that's okay. Um, yeah, so I'll send the slides like right after. So you can just like click on this video. And the most important part of the video for this particular question is minutes 1 to 5. So yeah, so that will basically explain the reason why the pressure is actually less in the narrow valve entrance. So yeah, but I do recommend watching the full video. I am not sure how to share my audio though, which is a pity. It's a really good video though. I do recommend watching it. Okay, so let us continue with the same passage. And so this one is during the efflux phase, CD, what is the pressure in the narrower valve entrance compared to the wider chamber? And so efflux is when the blood is flowing out. And so it's the third image. And on the pressure volume diagram, you can see that the pressure is remaining constant. So that should give you a very broad hint of what the answer is to this question. So I'll just give you 30 seconds to think about this, and then we'll talk about the reason why the answer is what it is. Okay, so let's talk about this. Okay, so I mentioned before that if you look at this diagram, CD, you can see that the pressure is very, very nearly constant. And so that means that the pressure in the narrower valve entrance compared to the wider chamber is actually equal. And this is because the blood can actually flow out. And because the blood can actually flow out, then instead of taking like Bernoulli's system as only like this this small section of the ventricle plus the valve, we can actually take this entire system to basically be blood flowing through the body. And because of that, there's like little change in pressure as the heart is contracting. Okay, and I also need to mention Pascal's principle, and that's pressure changes are transmitted equally throughout static fluid. And so the reason why we can consider this static fluid is because even though it's moving, like it's just like constantly moving like all over the body. And so that's why we can consider it static. And so pressure changes can actually be transmitted equally throughout the entire fluid. And so because pressure changes can be transmitted equally, that means that the pressure at the narrow valve entrance and the wider chamber are pretty much equal. Okay, this is a video on the cardiac pressure volume curve. So it's basically explaining like each step of the cardiac cycle as blood flows through the ventricle and out through the mitral and aortic. It flows into the ventricle through the mitral valve and out through the aortic valve, and how that relates to the pressure volume graph. So it's a pretty short video, and I really do recommend watching it just so you get an understanding of that entire cycle. Okay, so we're still on the same passage. And the question here is, during which segment of the cycle does the mechanical potential energy of the heart increase? Okay, so as we read this question, like we can actually use Bernoulli's principle for this. Like if you watch the video on Bernoulli's principle, they actually do mention how we can relate potential kinetic and hydrostatic energy or hydrostatic energy to pressure and density and volume as liquid flows. However, we do not need to use that principle. We can also just think about this conceptually to get the answer. So yeah, so just like look at each phase of the diagram of the 4 phases of the cardiac cycle and think about when you think that the most energy is being stored, because potential energy is basically stored energy. And so yeah, just look at this and think about which phase in which the most energy is stored and why that energy is being stored. So yeah, I'll just give you about 30 seconds to do this. Okay, now let's talk about this. Okay, so the answer is BC. So BC is the second image, and it's when both valves are closed and the ventricle is contracting. And so this should make sense to you. As the ventricle is contracting, like they're basically increasing the pressure, right? And they're increasing the pressure so that when the valve eventually opens, it can rapidly efflux out of the ventricle and through the aortic valve. In the first paragraph, they actually mention how the system of the left ventricle can be modeled as a single chamber pump attached to 2 pressure activated one-way valves. So you can just think of it as like basically increasing the pressure at BC, increasing it until the aortic valve opens. And so when the aortic valve opens, that's basically when the potential energy turns to kinetic energy as the blood rapidly effluxes out into the aorta. And so, yeah, so this is basically what it says. During the pressurization phase in BC, as the pressure is increasing, we're basically increasing mechanical potential energy, and so that it can be released as kinetic energy during CD, when the aortic valve opens due to the increase in pressure and the blood can go out of the left ventricle. Okay, so we only have one more question on this passage. I'm sure you're tired of this passage by now, but yeah, so we only have this one question left. And so this question doesn't really require you to know anything about this passage or the cardiac pressure volume curve in specific, but it does require you to know the principles of a pressure volume graph, like what that graph is and what it represents. If you already completed your physics review, then you should have at least some understanding of what this graph is and also the relationship between one of these terms here given in the answer choices to pressure and volume. So yeah, if you haven't finished your physics review though, you may not know this, but it's okay. We'll talk about this together after. Okay, so I'll just give you like 30 seconds again to think about this. Okay, let's move on to the answer. Okay, so basically the area enclosed by the loop represents the total work. And so we can think about this as the relationship between work and the pressure volume curve. So our standard definition of work that most of us learned in school is that work equals force times distance sine theta. However, work can also be modeled as a relationship between pressure times the change in volume. And so the equation is just negative pressure times volume change. And so in the pressure volume graph, this can be shown as the area under the pressure volume curve. And if you actually looked at this graph and calculated each section of the graph, you will find that the area that's enclosed by the loop is the work. So yeah, it's a pretty simple relationship, but it is important to know. Okay. So now we can finally move on to our second question, and this is on ideal gases. So I think that this passage is a bit simpler. However, it does require you to know some very key concepts in both thermochemistry and key concepts on how ideal gases behave. So just as a reminder, ideal gases are gases that are basically compressible. And there's several principles. There's actually in one of these videos. But yeah, ideal gases have no friction. They can move without touching each other. And yeah, and they have no mass. So yeah, those are the key principles of ideal gases. Yeah, so I'll give you like a minute to read this question and then we'll talk about the question. Okay, so I think that's about a minute. So basically the key part of this question is basically nothing in the passage actually. Everything that you need to know to answer this question is in this one table. And actually this is true for all of the questions that come from this passage. So yeah, this is just a tip for the MCAT. Just take a glance through the question before you read the passage, just to see how much of the passage you actually need, and then you also know which key parts of the passage to focus on as you're answering the question. But yeah, okay, so the first question is, what would be the correct ranking of the average kinetic energy of the gas molecules in the gases based on how they are labeled? The label is just each of these values in the table. Okay, so they're basically just asking the difference in the kinetic energy of the gas molecules. And to do this, we can use the ideal gas law. So kinetic energy is actually in the ideal gas law. However, it's not in the form that we normally think of kinetic energy. So temperature is actually a measure of kinetic energy. Therefore, because all the elements are gases, we can use the ideal gas law to solve this problem. If all of these elements were not gases, it would be a lot more complex of a problem. However, these are all noble gases. Just as a reminder, noble gases have complete electron configuration, so they are the most stable type of gas, just as a reminder from earlier chapters. Okay, so we can use the ideal gas law to solve this problem. So this is the ideal gas law, PV equals nRT. So know this equation and the relationships associated with it. This is an incredibly important equation, and you are almost 100% going to see a question that has something related to the ideal gas law on the MCAT. So yeah, it is an incredibly important equation. So P is pressure, V is volume, N equals number of moles, R is the ideal gas constant, and T equals temperature. So R is normally given to you, but make sure you look at the units of R because there's actually two types of the gas constant that they may use. And so, yeah, just make sure you take a look at the units that they're using. And you can use that to solve the problem. But for this particular problem, we actually do not need to know the value of R. And all we need to do is basically look at the relationships between pressure, volume, moles, and temperature. As a reminder, temperature is a measure of kinetic energy. So we can simplify the numbers used in this question and focus on the relationships in the law. And sorry, I should say we do not need to use R. I will correct that on the slides. Yeah, so we do not need to use R, and we can also simplify each of these numbers to make our lives much easier. So for helium, we can just do, instead of 100,000, we can just do 1. For volume, we can just use 2. And for moles, we can just use 4. And so if you calculate this without using R, just remember we're only talking about the relationships here. Like this isn't the actual temperature. We get 1/2. We can do the same thing for argon. 2 times 4 equals 8 times T. And we get T equals 1. For krypton, 3 times 6 equals 1 times T. So T equals 18. And then xenon, 4 times 8 equals 2 times T. And that basically means that T equals 16. And yeah, once again, this is not like the real temperature. This is just like our simplified relationship using the ideal gas law. And so from this, we can see that krypton has the highest temperature or the highest kinetic energy. After that, it's xenon, then argon, and then helium. And if we go back here, we can see that that's the answer. Krypton has the highest kinetic energy, followed by xenon, then argon, and then helium. So yeah, just know the ideal gas law and always remember to simplify the question to make your lives easier. Just remember that time is of the essence on the MCAT, although I'm sure you guys all know that very well by now. Okay, so the second question based on this passage is what would happen to the temperature of the helium container if the number of moles was kept constant, but the pressure was changed to 400,000 pascals and the volume of the canister was changed to 0.01 0.01 meters cubed. Okay, so once again, remember the ideal gas law, PV equals nRT, and remember our simplified relationships, and that should be enough to solve this problem. So yeah, I'll just give you like 30 seconds. Okay, now let's go over this together. So the answer is C, the temperature would double. And you will need to take into account basically both the pressure and the volume and their relationship to the temperature. And so remember the ideal gas law. PV equals nRT. All we care about right now is P and V and T, I guess. So we're quadrupling P basically. However, we're halving V. And so that's 4 times 1/2, that equals 2. And because of that, the temperature actually doubles. So yeah, the pressure quadruples, but the volume is cut in half. So therefore, the temperature doubles. Okay, now the third question based on this passage is, how much greater is the average kinetic energy of the molecules of xenon compared to argon? So just remember, temperature is basically a measure of kinetic energy. And so you can actually use the ideal gas law for this problem. And it's basically the same sort of technique with the same simplifications that we can use to solve this. So I'll just give you 30 seconds to work on that, and then we'll move on. Okay, so the answer is 16 times larger, which is B. And so we can basically just use the same relationship. Temperature is a measure of kinetic energy, so we can again use our simplification. So argon, 2 times 4 equals 8T, so that means T equals 1. Xenon, 4 times 8 equals 2T, therefore T equals 16. And you can see very clearly that T is therefore 16 times larger in xenon than in argon. And because T is a measure of kinetic energy, we can apply that to this question. Okay, so this one we're moving a little bit away from the ideal gas law and into heat capacities. So how would you rank the heat capacities of the gases at a constant volume? So to answer this, you should have an understanding of what heat capacity is, and also how it affects, and also how gases' heat capacity is affected. So we'll talk about what heat capacity is in the next slide, but just for now, just in case you know, I will give you 30 seconds to think about this question. Okay, so let us move on to the answer. So the answer is argon, then helium, then xenon, and then krypton. And so if you're only thinking about heat as a function of temperature, then you might be surprised by this answer, but we do have to consider, but there are some separate equations for heat capacity that we have to use for questions like this. Okay, but just as a rule of thumb, when you're answering questions like these and you see something about heat capacities of gases, just remember that heat capacity only depends on the number of moles of the gases available. And so therefore, it doesn't matter like the specific characteristics of the gas or the pressure or the volume. All that matters is the number of moles of the gas that are in the container. And so argon has the most moles, so therefore it has the highest heat capacity. And krypton has only 1 mole, so therefore it has the lowest heat capacity. Okay, but heat capacity is basically the ratio of absorbed heat to temperature change. And so basically all that means is how much heat does the substance need to absorb to change its temperature? And so the equation is heat capacity equals Q over delta T. So Q is basically the amount of absorbed heat, and delta T is the temperature change. So basically, this measures how quickly a substance can change its temperature. And therefore, if more energy is required or more heat is required, then the temperature changes slowly with the addition of energy. But if less energy is required, then the temperature changes quickly. And we can see this relationship as we look at this equation. So we see right here that Q, which is a measure of heat energy, if Q is large, then the heat capacity is large. But if Q is small, or the amount of heat that needs to be absorbed is small, then the heat capacity is also small. And Q, and so yeah, that's basically what it is. Oh yeah, and Q and delta T also have a direct relationship. So that means if Q is large, then delta T is also large. So if less energy, okay, sorry. So you might also see specific heat capacity, and that is the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or Kelvin. And it is measured in calories per gram. And so you might see specific heat capacity, like for example, of water on the MCAT. So just keep that in mind, that it's basically just the amount of energy required to raise temperature by 1 degree. Just as an aside, Celsius and Kelvin have basically the same relationship in terms of degrees. It's just that Celsius starts from the freezing point of water, which is 0 degrees Celsius, while Kelvin starts from absolute zero, which is like basically the lowest temperature can go. And it's almost, I think it's theoretical actually, because I don't think they've found anything that can go to actually absolute zero. But yeah, so Kelvin is, so to convert from Kelvin to Celsius is basically just adding like 273 degrees to the Kelvin temperature to get the Celsius temperature, because 0 degrees Celsius is 273 degrees Kelvin. So yeah, that's just like an aside that you should keep in mind, because you may need to convert between units on the MCAT. But anyways, for this particular problem, all we need to know is that the heat capacity at a constant pressure of a monoatomic ideal gas is 5nR over 2. And so on the MCAT, we mostly only care about the relationship between the variables. And so from this equation, we can see that the only real variable is n, which is the number of moles. R is the ideal gas constant. So yeah, only the number of moles matter. And for that reason, argon, which has 8 moles, has the highest heat capacity. Okay, so the second question is also a heat capacity question. And so just remember the principles of heat capacity that we talked about while you are looking at this question. And so basically it's that you decide to add the same amount of heat to each canister and allow the canisters to expand so the pressure of the gas remains constant while the heat is added. So during this process, which gas would change its temperature by the greatest amount? So basically temperature is constant. Pressure is constant, but temperature is increasing. So I'll just give you 30 seconds to look at this question, and then we will go over the answer. And also, this is the last question. So great job for sticking through. Okay, so I think it's been about 30 seconds. So let's see what the answer is. And the answer is actually krypton. And so to answer this question, we basically have to think about what exactly heat capacity is and what its relationship to temperature change is. So heat capacity is the amount of heat needed to change the temperature. And so krypton has the lowest heat capacity. So it needs the lowest amount of heat to change its temperature out of all of these gases. And so as more temperature is added, because krypton doesn't need that much heat to change its temperature, it actually changes its temperature by the greatest amount. So yeah, that's basically what this says. It has the lowest number of moles and therefore the lowest heat capacity, and therefore it changes its temperature the most. Okay, this is a great video on both calorimetry and thermochemistry, and it goes through both problems and also the principles of calorimetry and thermochemistry. So calorimetry is basically like the measure of heat capacity, and thermochemistry is just like, temperature change, and how that relates to enthalpy and entropy. So enthalpy is like the change in heat in a system, and entropy is the change in disorder of a system. So yeah, I would definitely recommend looking at this video so you basically get that content review aspect. So yeah, so that is the review session today. It is a bit shorter, and that's because like this is kind of like a new thing for me, since in the past we basically focused on content review and we didn't really talk about MCAT questions, and instead we focused on like short questions that basically help explain the concepts that we talked about. But hopefully like this type of video is more useful because you can basically find the exact same content in your Kaplan book or in videos like this. So hopefully this was a bit more useful. But yeah, let me know if like you have any suggestions or if you think like this is stupid and we should go back to just doing content review.